Boris, nice to see you. How are you doing? Let us recall our last lecture. So we introduced electric field and claimed that electric field is a substance which electrical charges can interact with each other without being in direct contact. So we derive equation which helps us to calculate strengths of electric field next to point charges. Welcome. And then we also step by step went to different cases, considered opportunities to calculate electrical field next to a system of point charges. So when you just determine individually contributions of each electrical charge to electrical field in a given point of space, and sum up in a vector form electric field vectors created by each of these point charges. And eventually we came up to so-called continuum of electric charges when electric charges are placed very close to each other. So distance between these point charges is much smaller than the distance from them to point where we want to determine electric field. So taking into account these conditions, we already cannot distinguish between different individual point charges. We consider them as a continuum. Can you remind me which kind of continuum of electric charges we consider? There are in terms of dimensions. Linear surface, like two-dimensional, and three-dimensional bulk. So we have specific parameters which describe density of electric charge. So it's either rho tells us coulomb per cubic centimeter. So it's obviously for three-dimensional continuum of electric charges. And we have sigma, which gives us coulomb per square centimeter, and lambda, which is the linear density of electric charge distributed along a straight or some curved line. It could be some wire or whatever. So taking this into account, we also consider some example how to calculate electric field next to a rod, where we have uniform distribution of electric charge. So today we proceed further and we introduce Gauss' law. So that's our goal for today's discussion. And obviously, in order to do that, first we need to introduce the concept of electric field flux. So when we have some vector field, which is in our case electrical field, it's described by electric field vector at any point of space, and we have some surface, we can calculate so-called electric field flux through a given surface. So if we have perpendicular orientation of surface with respect to the electric field vector, so in that case, such flux can be determined in a very simple way. It's actually product of magnitude of electric field vector and area of a considered surface. So if we have, let's say this is our electric field vector, and here is the surface. So it's cross section because surface is perpendicular to the electric field vector. Here we have 90 degrees. So this surface is characterized by some area A, and in this case we can write that flux of electric field is equal to the product magnitude of electric field vector and area of the surface. However, that's not always the case. Obviously, this surface can be oriented in arbitrary way with respect to electric field vector. And in this case, when we have some, better to draw some surface, here is our electric field vector. And here is normal to the surface. So then we consider this angle alpha, and in this case, electric field flux can be determined as magnitude of electric field times area times cosinus alpha. So here, this part can be considered as equivalent of this surface in the direction perpendicular to electric field vector. So that is general definition how we determine flux of electric field. However, the thing is that not always electric field is uniform. So we need to take into account that the magnitude and also orientation of electric field vector may change from point to point within this surface where we want to determine electric field flux. So usual approach how we deal with this, we divide this surface in very small elements and consider um, uh, electric field flux through each of them. They should be as small to allow us to consider electric field vector uniform within this small area. So we need to introduce some vector delta A vector, which is area of this small element times unit vector of its normal, normal to this small area surface element. So once we have this introduced, we can express that flux of electric field through this small element I will be given as electric field magnitude next to this small element EI times delta AI, which is the area of this small element. And obviously here should be cosinus, let's say theta I. So this is the angle between the electric field vector at this small element and the normal to the small element surface. So this can be represented in a different, more convenient and shorter form. Any suggestions what this could be? We considered during last semester some operations on vectors. Does it look familiar to you? Vector multiplication, and which vector multiplication? I. Well, we have two options. We have either scalar or vector multiplication. Scalar. So that is nothing else as a scalar product of two vectors. This will be EI vector, and here, or dot product, delta A vector. So this is this vector which we introduced. So now, if we want to get total flux through the surface in the case when electric field is not uniform. We need to sum up electric field fluxes through all of these small elements. So total flux of electric field will be equal to sum over all elements I, and here will be scalar product EI vector times delta A vector. So that is the um, general representation. However, if we consider that small area A is approaching 0, so we have a limit condition, then this sum is transforming to a integral over surface. So it will be integral over the surface. Here will be our scalar product of electric field vector dA vector. So what is also important to mention here when we introduce this concept of electric field flux, that we may have closed surface. So any suggestion, what is a closed surface? So we could consider any surface of a three-dimensional body as a closed surface. So closed surface divides space into internal space, which is included into this closed surface, and external, which is outside. So if we want to determine electric field flux over a closed surface, we need to integrate this. We show this surface integral as over a closed surface. So that's important because that's actually the goal, the key feature of Gauss' law to eventually find electric field fluxes through closed surfaces. So in terms of the concept of electric field lines, how we can describe electric field flux. So in general, it would be electric field flux is proportional to the number of electric field lines which are entering the closed surface, and we need to take into account that if electric field line is entering closed surface, at some point it should go out this closed surface. So the net difference between entering and exerting electric field lines from closed surface will give us the net electric field flux through this surface. You may already think about this and understand that if the source of electric field or any other vector field is located outside of a closed surface, then it doesn't matter how it will be placed with respect to this closed surface. The net flux of this electric field created by the source we are considering will be equal to 0. So the net flux through a closed surface when the source of electric field is outside the closed surface, then it will be equal to 0, but we will show this on some examples. So let us consider a simple example when we have a closed surface in the form of a cylinder. So we have system of coordinates. So this will be x, y, and z. And let us change the color maybe. So this is our cylinder, which is placed along axis X. So here we can consider three surfaces of this cylinder. So it will be surface A1, A2, so these are bases of the cylinder, and the side surface will be A3. So here will be normal unit vector N1, here normal unit vector N2, and normal unit vector N3. Now let us assume that we have electric field vector oriented parallel to axis X. So it's some external electric field, and we place this closed surface in the form of cylinder with this configuration with respect to electric field, and want to determine electric field flux through this closed surface. So total electric field flux will be equal to sum for electric field flux through the first, second, and third surfaces, like parts of this closed surface. 2 plus 3. So let us consider first surface, electric field flux through first surface. That will be electric field times, we can write in vector form first, and that will be electric field times area of the first element of this closed surface times cosinus, not sinus, cosinus, and here we have pi. So these vectors, electric field vector and n1 unit vector, they are parallel to each other, but in opposite directions. So there is a 180 degrees between them. So what this will give us, not just one, minus one. So it will be minus E times A1. So that's the flux of the electric field vector E, which is considered here obviously as uniform through this element of the closed surface. As you see, it comes with negative sign, so we always need to keep in mind the relative orientation of the normal to the surface and electric field vector. So let us consider flux through second surface. That will be E vector times A2 vector, and that is E times A2 times cosinus. In this case, they are parallel and coincide in direction, so it will be 0. So that will give us just positive E times A2. And one more element of this closed surface, that is surface A3. Electric field flux through this surface will be E vector times A3 vector. That is E times A3 times cosinus. And here we have pi over 2 or 90 degrees. So that will give us 0, and we eventually have 0 flux through this side surface of the cylinder. So now, according to this previously defined equation, we find the total flux. And assuming that this is cylinder, so the left and right side of the cylinder, they should be the same. A1 should be equal to A2. In this case, total flux of electric field vector through the closed surface will be equal to 0, because these two components will compensate each other since they possess different signs. And in magnitude, they are opposite. So we see from this simple example that for a closed surface, uh, electric field flux is equal to 0 when we just place this closed surface in external electric field without, so that we will consider a little bit later, without any charges which are sources of electric field placed inside this closed surface. Obviously, there are some charges somewhere outside, because this external electric field should be created by something. So there should be some source of electric field which creates this uniform electric field E. Uh, However, this source is not located inside the closed surface, or is not enclosed by this surface of our consideration. So now we are coming finally to the Gauss law, and we will try to formulate it. So let us consider some positive charge, Q, and some sphere around this positive charge when positive charge is in the center of this sphere. So as much as I can show this symmetric sphere, not very symmetric, but let's assume that this is a sphere. And here we have radius r. Here. So we can consider a small surface element of this sphere with area, let's let it will be delta A, and here will be unit vector, unit normal vector, and electric field vector. So we know that point charge creates some spherical symmetry of electric field around it. So electric field vector will be oriented, like pointed away from positive charge. So it will go like this direction, and it will be always perpendicular to the surface of the sphere, taking into account the symmetry of electric field created by a point charge. So that's why unit vector of each small element which we consider on this sphere will be always parallel to the electric field vector. So now let us consider, like, let's say, taking into account that they are parallel to each other, we can write that E vector dot product delta delta A vector can be replaced by product of their magnitudes. So it will be E times delta A. Now, again, now we determine electric field flux through whole this sphere, which surrounds encircles electric charge Q, positive electric charge Q. So in this case, it will be integral over closed surface. And here we have, as we defined earlier for electric field flux through a closed surface, vector product of electric field vector and dA vector. So we take into account that at any point they are parallel to each other. So we can write here that it will be integral all over the surface, this surface of the sphere, of E times dA. So we don't need vectors anymore here. And what we can do with electric field, we can actually factor it out from the integral, because no matter which point on this surface we pick up, electric field will be the same. Again, because of spherical symmetry of electric field created by a point charge. So we can factor out this electric field here, integral dA. Okay, so now who will remind me what is the equation which allows us to calculate magnitude of electric field next to a point charge? Ke, which is electric constant, times what? Q divided R squared. So that what we derived last lecture, and it definitely is applicable to our case today. So we know electric field, which is uniform at any point which we can pick up on this surface. Now, any suggestions what this integral over the surface, like closed surface, will give us? What it should be? So if we divide some closed surface in small elements, and integral over these small elements means that we add up all small elements together. So what it will give us? Area of the sphere. So it will give us the area of this sphere. So what is the equation for area of a sphere? Oh, that is for volume, but for surface it will be 4 pi r squared. So now we have both components of this electric field flux. So let's put this together. So we have electric field flux through this closed surface. It will be Ke times Q times R squared. And instead of integral, we have 4 pi times R squared. So we cancel out radius, and we have 4 pi Ke times Q. Now we can recall that electric constant Ke is equal to 4 pi divided like 1 over 4 pi times epsilon naught, which is the permittivity of free space. So taking into account this, we can write that it will be equal to Q divided by epsilon naught. So the total net flux of electric field created by this positive charge encircled in some sphere will be equal to magnitude of this electric charge divided by some universal constant, the permittivity of free space. So in general, we can write that this equation clearly tells us that electric field flux is directly proportional to the magnitude of this electric charge inside the sphere. So now we make one more step and consider that we have positive charge, and let's say we have some sphere, and then we have some arbitrary shape, three-dimensional closed surface around this system. So we have charge and two surfaces, closed surfaces. One is spherical, which we considered previously. Another is arbitrary shape. So we mentioned earlier that the magnitude of electric field flux will be proportional, or in other words can be also said that will be defined by the number of electric field lines which goes through this surface. And earlier, like during previous lecture, we also mentioned that the number of electric field lines which originate at each positive charge, because if it's negative charge, electric field lines terminate on it. So we are talking about positive charge at this point. So the number of electric field lines which originate and are coming out of it will be proportional to electric charge. So we have quite defined electric charge. Let's say it's some charge Q. That means we will have defined number of electric field lines which are coming out from this charge. So let's say that the magnitude of this electric charge is enough to create these 4 electric field lines. What is the flux of electric field created by this positive charge through the spherical internal closed surface in terms of number of electric lines? So we can count them. There are 4 electric field lines are going through, so they're coming outside from the closed surface, spherical surface. At the same time, we can make the same statement for any other closed surface, regardless of its shape. It can be spherical or it can be any arbitrary shape. We also have 4 electric field lines which are coming out from this closed surface. So that means that it does not depend on the shape of the closed surface. What really matters, that's the amount, like magnitude of electric charge, which is enclosed inside any closed surface. So that will define the electric field flux, and it will be equal, as we derived earlier for a spherical surface. Can write it down here. Electric field flux through a closed surface of any shape will be equal to electric charge enclosed in this surface, and also need to take into account permittivity of free space. So that is the definition of Gauss law, and with this we definitely can proceed further in terms of calculating electric fields created by more sophisticated continuums of electric charges. So in order to summarize this, we can consider one thing more, which is again electric field flux in terms of electric lines through a closed surface when electric charge is placed outside the surface. So let's say we have a positive charge and some arbitrary shape closed surface next to it. So now we don't have any charges inside the surface, and this charge creates some electric field lines which go inside and outside the closed surface. So here is like electric field lines, 1, 2, 3. So also quite clear example, we have 3 electric field lines which are coming inside the closed surface, 3 which are coming outside. So the net total electric field flux will be equal to 0 because they compensate each other, and net amount of electric field lines which are coming out from the surface will be equal to 0. So now let us consider a simple example when we have 3 surfaces. Surface 1, or maybe let's mark it as 1. Then it will be some surface 2, and here will be some surface 3. And we will place some charges. So it will be negative charge Q1. Here will be positive charge Q2 and negative charge Q3. And somewhere here we will place positive charge Q4. So now let us consider surface 1. What will be the uh, electric field flux through surface 1? Q1 over epsilon naught. So we write here that theta, like this flux over through closed surface 1 will be equal to Q1 over epsilon naught. We need to keep in mind that here it will be smaller than 0 because charge is negative. So in similar manner, we can write electric field flux through surface 2, phi 2, and that will be Q2 plus Q3 divided by epsilon naught. So that will be either larger or smaller than 0, so positive or negative, depends on magnitude of positive and negative charges enclosed in this surface. So what will be electric field flux through surface S3? So neither these charges which are enclosed in other surfaces, nor charge which is somewhere outside, which is charge Q4, will not create any net electric field flux through surface S3, since inside we don't have any charges. So that will be equal to 0. And here it's important to highlight one thing. It's not because at any point of this um, closed surface, electric field vector will be equal to 0, because that could be also an option. So if we divide this surface in small elements, and next to each small element, electric field vector is equal to 0, then net electric field flux will be also equal to 0. However, not in this case, because that would be true if we don't have any charges here. So then we don't have sources of electric field. We actually don't have electric field, and non-existent electric field flux will be equal to 0. However, here we have some net electric field vector created at each of these points by all of these charges. So, and this electric field vector will be not equal to zero. However, the net electric field flux through the surface, closed surface, which does not enclose any charges inside it, will be equal to zero. So that you should understand that zero results in compensation of electric field fluxes through all electric field vectors at each of the point of the surface, not just because there is no electric field at the surface we are considering. So now when we have um, clear understanding of the Gauss law, uh, so how would you formulate Gauss law now? Any suggestions? Electric field flux through a closed surface.
Directly proportional to the magnitude of the uh,
Electric charge
electric charge.
enclosed in this surface. Yes, so then we need to only operate also with the universal constant epsilon naught. Later we will consider also that if that is happening in some medium, we need to take into account properties of the medium. So there will be also the electric constant, but we will introduce it a bit later. So now let us summarize our discussion. So we introduce the concept of electric field flux. We know that it is defined as the product of electric field magnitude, area of the surface, and we need to multiply it by cosine angle between the electric field vector and normal to the surface. If electric field is not uniform, in that case we need to take into account that its magnitude and orientation is changing as we go from one point of the surface to another. So in this case, we divide it into small elements. We find electric field fluxes through small elements where we can consider electric field vector as constant, and then we sum it up. So eventually, if we consider very small surface elements, we end up with an integral over surface of electric field vector dot product dA vector, where dA vector is small area times unit normal vector of this small area segment. So that is the general definition of electric field flux. And we have shown on a clear example with a positive charge inside in the center of a spherical closed surface that the total electric field flux, the net electric field flux through this surface will be defined by the magnitude of electric charge divided by permittivity of free space epsilon naught. So that is the definition of Gauss law, which tells that electric field flux is proportional to the magnitude of electric charge placed in this inside this closed surface. So if we have multiple charges, then we need to have to calculate the net electric charge enclosed in this surface, and of course take into account the sign of each charges which are placed there. So we will continue next lecture with application of Gauss law, and you will see that it will not always, unfortunately, but at some cases which satisfy certain conditions, it will be really a neat technique to calculate electric field of continuum electric charges. Instead of doing some complicated integration calculations, integrate over length or surface or volume, depends what kind of continuous electric charges you are dealing with, it will be possible to apply the concept of Gauss law in order to determine in a simple way electric field magnitude of electric field vector of such continuum electric charges. So see you next time on Wednesday. Thank you very much for attention and have a good day.